Today we have Michelle Lastrina, who will be presenting about can you paint yourself into a corner looking at graph theory and colorings. And go ahead whenever you're ready.
Thank you for the introduction. So, to give you kind of an outline of what we'll be looking at today, to make sure everyone has the same background, we'll just go over an overview of graph theory and some basic graph coloring, and then look at coloring extensions. And then from there we'll transition into list coloring, which is what I study, and extending list colorings on planar graphs, and then kind of look at where we can go based on the results presented. So a graph is a pair of vertices and edges, where the edges are just a subset, or are just a subset of the product. So edges are just ordered pairs of elements from the vertex set. So as kind of a little example, if we think of the vertices of this graph are just the numbered circles, and all the edges between them, or all the lines connecting them, are the edges. We say that two vertices U and V are adjacent, denoted using a tilde, if the ordered pair UV is an element of the set V. So in this particular graph, we would say that 1 is adjacent to 4, depending on the vertex. So if we have a graph G and a subset of vertices U, if we take that set and all of the edges whose endpoints are both elements of U, we call that the subgraph induced by U. We can also have subgraphs that are not induced by U, they would just not have as many edges. So for example here, the subgraph induced by, say, 1, 2, and 4 would just be this portion here, but nothing else. We define the distance between two vertices in a graph to be the length of the shortest path between them. Okay, so a path between them would just be going along the vertices and edges to get to the other. So for example, the distance between 1 and 6 would be 1, 2, 3. We say that a graph G is planar if it can be embedded in the plane. So in other words, you can just draw it on a piece of paper with none of the edges crossing. So for example, the two graphs on the left-hand side are actually the same graph, just drawn differently. Okay. On the left, it appears to not be planar, but we can actually redraw it moving around the vertices so that it is planar. However, the graph on the far right is non-planar. There's no way to draw it so that we don't get edges crossing. Okay, so now to talk a little bit about coloring, a vertex coloring, or more generally referred to as a coloring of a graph, is an assignment of colors to vertices of G so that two adjacent vertices don't get assigned the same color. If we use colors 1 through K, we call that a K coloring. And we define the chromatic number chi of G to be the smallest integer K such that a K coloring exists. Okay, so we would also say that a graph is K colorable if its chromatic number is at most K. And in some cases, you do also see edge colorings of graphs, but here we'll be talking about vertex colorings. So for example, this graph is known as the Peterson graph, and this coloring of the vertices shows that it's 3 colorable. And in fact, its chromatic number is 3 because, if you just kind of look at it a little, you can see that 2 colors would not be enough. So one kind of famous result in graph coloring on planar graphs is the four-color theorem. And that dates back to 1852. And it was originally stated as if you have any separation of a plane into contiguous regions called a map. The regions can be colored using at most four colors, so no two adjacent regions get the same color. And for these purposes, we say two regions are adjacent only if they share a border segment, not just one. So, this is sometimes referred to as the four-map color theorem because we can kind of think of this as just trying to color a map using only four colors. So, for example, this would be a four coloring of the 50 United States. So how does this relate to vertex coloring? We can actually restate this in a much easier way. And by letting the regions represent vertices of a graph, and if the regions are adjacent, we put an edge between those two vertices on the graph. And so we can restate this to say that any planar graph is four-colored. So if we translate that map we looked at of the 50 United States into a graph, we would get something like this. So if we translated those four-colored regions or the states into colors assigned to these vertices, we would have a four coloring of the graph. And in fact, three colors are not enough in all cases. So. And just to give you a kind of idea of the history of this theorem, I think it's kind of interesting. So it was originally posed in 1852 by Francis Guthrie. It was actually originally credited to De Morgan because I think Guthrie's brother was working under De Morgan, so he ended up originally posing it in a letter. And so that was in 1852. So then in 1879, Kemp came up with a proof that 11 years later was shown incorrect. By Haywood. And in fact, also at that same time, Haywood came up with a proof of the five-color theorem, which is the same thing except showing that five colors are not. Similarly, in 1880, Tate came up with a proof that then 11 years later was shown to be false by Peterson. Okay, so that's kind of an ongoing pattern. In 1943, we were introduced to the Heidegger conjecture, which is a generalization of the four-color theorem, and that's still open today. And then as time went on, one thing that came into play with the proof was proof by computer. So in the 1960s and 70s, people started trying to use computers to prove theorems. So for example, in this case, they started looking at trying to find a counterexample on the fewest number of vertices and constructing that with a computer. So they weren't able to complete the proof during that time period, but in 76, Appel and Hawken came up with a proof based on that same idea, showing that no counterexample on the fewest number of vertices existed. And what they did was kind of look at two different main ideas. They came up with an unavoidable set of configurations, so these kind of subgraphs that would have to be part of the graph if we were unable to color it, and then showing that you ran into them. And then also showing that there are some subgraphs that we can assume are not in the graph, because if they are, we could color the rest of this minimal counterexample and then be able to color this remaining kind of little part as well. So those are the two kind of main ideas behind it. So they came out with that, and then in the 1980s, Schmidt and some others found some errors, but they were fixable. And around 1989, they published a complete and detailed book. I think it's like 300 pages or something like that, describing everything. And so I think for the computer program they're running isn't like based on a Cortex